good afternoon, everyone. It's 10 past 3. Welcome to this week's live stream for the lecture session of the course PLFM, Programming Languages and Formal Methods. As you know, this is the last lecture session of this course. Every year, as I do every year, I typically like to have a guest speaker this at the last week of the course. And this week, I'm really happy to have Andreas Lochbihler here to present this guest lecture. So Andreas has been working at Digital Asset for about 2.5 years. And this is one of the companies that really uses the technology that we have taken a look at in this course. So typically functional programming, formal methods, really impressive and complicated thing. So I'm really happy that Andreas is here. Andreas and I come from the same sort of background. Both of us are interested in functional programming, formal verification. Particularly, Andreas is interested in security aspects of software. Yeah. And yeah, I'm really happy that he could be with us today. Martin, unfortunately, is unwell today, and therefore Andreas has very kindly offered to also fill in for him. So he will be actually doing both parts of this lecture today. So before I start, I'd just like to mention that this lecture will be recorded for the people who can't make it, firstly, and also I would like to allow Digital Asset permission to use this video for their internal whatever marketing or tutorials. Problem with this, you don't have to share your video or share your name when asking questions and things like that. But as always, so we're doing this on MS Teams so that you can also speak up in the middle of the lecture if you want to answer a question. And in case you do have a question, you can also write in the chat in Teams this time. Andreas will not be able to see these questions, but I will relay them to him. Yeah. Does anyone have any questions regarding the technical or formal aspects of today's guest lecture? You can write in the comments. No. What else? So regarding how today's lecture session will take place. So Andreas will talk about Daml and then about Canton. Sometime around 4, I would like to have a formal course where I'll talk a little bit about the examination and also round it off and just talk a little bit about the topics. And I'd like to have a little bit of feedback from you. So at around 4:30, we will start this formal conclusion of the course, and it should take about 20 minutes, 15 to 20 minutes. Yeah, but yeah, that's for later. In case we need more time for this guest lecture, Andreas is very kindly offered to prolong questions, discussions, and also some of the material at about from about 5 o'clock, at the exercise session from about 5 o'clock. But don't worry, in case you can't make it for that, it will be recorded and available for you later. Great. I think I mentioned everything. Did I forget anything, Andreas?
No, I think we're good. Thanks for the kind introduction, and hello everyone. Yeah, it's a pleasure to be able to talk about what we've been working on and looking at in the past years. So Digital Asset set out as a company to transform the how business is done between industries, and well, our two main results of that are basically Daml and Canton that I'm going to talk to you about today. The title is Enterprise Haskell on Distributed Ledger Technology, so Daml will be about the enterprise version of Haskell, and Canton will be how to actually run that on a distributed ledger. Yeah, please feel free to interrupt during the talk, ask questions if I'm going too fast or too slow, because I don't know what your background is. So it would be a pity if this talk just rushes by you because you got lost on page 2. So let's try to make this as interactive as possible. Let's start with the first talk, namely Daml, which is Enterprise Haskell. And for that, just a brief intro. What are we actually looking at here? So some of you might have heard of Bitcoin smart contracts, maybe used that yourself already, maybe run a Bitcoin node if you want to. And one of the big goals of this blockchain people is essentially to eliminate trust. So Bitcoin's goal was to create trustless money. What does that mean? Well, money in the sense of cash, like unlike your bank account where you have to trust your bank that the bank correctly manages your funds. Money as in the form of cash, well, it's just the banknote, the bill, and you can go to a shop and the shop will accept it. You don't have to reveal your identity and nobody will be able to track what you have spent for your money, basically. And for Bitcoin, this is basically the same goal there. They wanted to create this kind of bearer token money where you just have to present, here is my cryptographic hash, and everyone will happily accept that. The difference with normal money is that we don't have a central bank with Bitcoin. So there's nobody that we have to trust with the monetary policy. That's encoded in the algorithms behind Bitcoin. Now, the algorithms around Bitcoin, they were mostly about managing this money. Ethereum then went one step further and added a Turing-complete programming language around the idea of running things on a blockchain. So now we have trustless Ether money, and we have trustless and unstoppable contracts. So there's no individual party that could stop them. They will just keep plowing on, following their code, as long as there are still nodes running the Ethereum network. This trustless approach works nicely if you have purely trustless goods, such as the bearer tokens. But as soon as the data that you store on there has actually some connection to the real world, this connection will always be rooted in the trust, in some trust, and it will never be unstoppable. And that's where we're coming from. So this is not about the Bitcoin classic, the classic Bitcoin, let's eliminate all trust. To see why this happens, let's have a look at a classic example, the smart card lock by Nick Szabo. So the idea was, well, you want to buy a car, but you don't have enough money. So you go to the bank will give you a credit, and that credit allows you to buy the car and use it. Well, provided you pay the monthly installments to your credit. And that's essentially the collateral that the bank has. If you stop doing so, well, then the car will let you in, and this is encoded as a smart contract, right? And the car just has to provide evidence in some form that you didn't pay, and everything is fine. Now, as compelling as this example is, the problem with that is that, well, technically, the instruction produced by the smart contract that the car should now belong to the bank is just a piece of data, right? This piece of data needs to be interpreted by the car or by whatever entity that takes hold of the car and actually let you in. So we do have a root of trust, which in this case is car manufacturer. If the car manufacturer's software doesn't accept the smart contract's output, then the bank has no way to block the car. And that's why the whole thing is also stoppable. Because, well, we can exert pressure on or people can exert pressure on the car manufacturer to actually not follow that smart contract rule. And then There's no the code is the law approach there. So unlike the public blockchain setting, for an enterprise world, our thesis at Digital Asset is that, well, the benefit of a smart contract platform is not in eliminating trust, but in actually securely managing multi-party workflows. So this is a different setting in the mind. What does that mean? Well, and this will be the running example for the first half, we're considering that Martin, who's an enthusiast biker, needs to get his bike repaired. So we're looking at a workflow where Martin wants to get his bike repaired, and of course Martin wants to pay the bike shop for the repair, and so we also involve a bank for dealing with the money transfer. So we have several parties here, the green boxes, and they have a joint workflow. Now, that joint workflow operates on some shared state that involves Martin's bank account, that involves the contract between the bike shop and Martin, that involves the bike shop's bank account, and possibly a lot more stuff. And we can imagine that being stored in a shared database, or what we call the virtual global ledger. And Martin and the bank and the bike shop, they can advance this workflow by writing to the database. And it will be notified by the database about updates to that global shared state. That's the mental model that we have. So shared database, virtual global ledger, that sounds good. But of course, there are a number of issues we want to look at or want to take care of. First of all, we need to properly deal with authorization. The reason for that is, well, Martin just doesn't want the bike shop to fiddle with its bank account other than for paying the invoice. Conversely, the bike shop doesn't want the bank to have a say in whether they will have a contract or not. Then we also need confidentiality and privacy. So maybe Martin doesn't want to tell the bank what he spends his money on. Conversely, the bike shop doesn't want to have Martin learn their balance on the account. And basically, yeah, we need access control here. Both for the data and maybe also for who's actually involved in a particular update. The third thing is we want to have some sort of transactionality. So you want to have, on the one hand side, well, you want to do atomic transactions. Say, if I want to exchange Swiss francs into euros, well, then I have to give Swiss banks to essentially whoever is interested in getting Swiss francs and get euros back. And that transfer of both monies, that should be atomic. So either both happen or none of them happen. In particular, I can't end up with having handed out the Swiss francs and not having received euros. That would be a bad deal for me. And conversely, my counterparty doesn't want to end up in a similar situation where they have handed out the euros, then something in the implementation went wrong, and I end up with both Swiss francs and euros. That would be great, right? But just for me. The other part is compositionality. So we want to have small building blocks like transfer of money, and then want to compose them into larger pieces, where we can do these atomic swaps composed of two individual transfers that will help us modularly decompose things and work nicely. And finally, we want the whole thing to scale, which we capture with global compositionality. The problem if we just have a single shared database is, unexpectedly, everything has to go through that single shared database. Now, maybe the bike shop also wants to do business with Andreas. And so we have another such a setup. And of course, ideally, we use the same shared database or the shared virtual global ledger. But, well, if that runs on a centralized instance, we can't scale that to a worldwide setup. So that's something we'll look into that. And this talk today, part 1, Daml, will take care of the 3 first challenges from a programming language perspective. And just by offering the right programming primitives, you get that. And then you need an implementation for the whole thing, and that is part 2, where I'll talk about Canton. As said, please feel free to interrupt me, ask any questions, whatever you like. I'm happy to help. Right, so what is Daml? Well, Daml is basically Haskell with a few changes that we've made. So some of them are just syntactic, and you'll see that in a minute when we'll do an interactive development. And some are semantics. The most important change is essentially we've given up the lazy evaluation regime of Haskell, and everything evaluates strictly. The motivation for that is basically to make it simpler to predict when things are actually evaluated, and also simpler to implement as a distributed system. And while starting with this core part of Haskell, we've then added a few primitives for talking about smart contracts, added the authorization rules that we need to track access in a distributed setting, and added the part, you only need to know, you only learn what you need to know. So this need to know privacy. If you're interested and want to try it out yourself, visit our webpage daml.com, where you can download the SDK. There's also a web ID if you want to try it out there. And if you have questions, we've just opened up the forum on discuss.daml.com. But we also have a Slack channel if you prefer talking there. Response times, I'd say, are similar on both sides. Now, this is just a programming language, and you then need some storage layer on which you actually run this thing. And in the simplest case, you would just pick a SQL database and run that in a centrally operated system. If you just want to do Daml on your own because you think this is a fantastic, great language to express workflows, you can do so. But you can also run it on things that support some sort of distribution, like Hyperledger Fabric as a blockchain, or the VMware Concord, which does Byzantine fault-tolerant replication. We've also got an integration with Corda and many more to come. So where is the whole thing actually used? Well, we've got a partner, Accenture, who has helped us build a lot of things. And few examples. So the Australian Stock Exchange has decided to renovate their clearing and settlement system, and that's going to be written in Daml. Hong Kong Exchange also is about to do a similar move. The ISTA gives us essentially standards for how to deal with financial instruments. So you see this is a lot of financial industry there. The reason is just very simple to digitize money, because nowadays most of the money anyway is done electronically. So that's very easy to transfer. The other part where Daml has an edge over other people is healthcare, because there you want to be very careful about who's allowed to see what data, and that's where the privacy and confidentiality confidentiality guarantees from Daml make a difference. Why that abstract? So there are use cases. They're getting more and more. So let's look a bit under the hood. This talk is not a marketing talk. So why did we pick Haskell? Because Haskell is not really the first choice if you go out and ask, oh, what is your favorite programming language? Those who know Haskell and know its benefits, they love it. But in industry, they ask different questions like, oh, what is the pool of available programmers? And I mean, you guys and girls, you know Haskell, you're in that pool, but that pool isn't big. So that might be already, especially, well, that pool is not big if you're looking for cheap labor. So that's a problem. So why did we nevertheless pick Haskell? Well, there were essentially three reasons. One reason, it has a very good type system. It's fairly expressive, it's strong. And a good type system, well, has certain benefits, as you might have noticed. So there's the famous saying by Robin Milner, type-safe programs cannot go wrong. And I'm aware that I'm using it a bit out of context, but it is known that, well, you can catch a lot of errors at compile time if you're very careful with the types that you're modeling. And the other part is, well, we're basically describing the data that we'll store in this shared database using Daml. So if we have a strong type system, then we can actually compile this into database data schemas. If we don't, then we need to come up with some unstructured data representation, which has its own drawbacks. But I mean, there are many languages with strong static type systems, so that's not the only part. Another idea was, okay, well, Haskell has a strong bias towards immutable data structures. And given that a distributed ledgers or a blockchain, they're all about immutable append-only logs. They just record updates to the state, and then you can reconstruct the current state by looking at the past, what has happened. So if you have immutable data structures, that's very nice, because then you don't have to make precautions that you accidentally modify them in your smart contract. And something that you might also have seen in the lecture is essentially that you can track side effects in the type system, so you can distinguish what is a pure expression and what are impure computations. The keyword here is a monad. So, you know, once you're in a monad, well, you can run it, and that's the only way to get out of the monad. But for example, you can't get out of the IO monad, and so you can control the places where you can have side effects and where you can't. And if you can eliminate side effects, then you know, well, along with the immutability stuff, we basically get deterministic computation. And in a distributed setting, that is a very valuable property. Because, well, if I run the smart contract code and realize, okay, this evaluates to the result 17, then I can send that, say, to Farhad, and Farhad then can just rerun the same program, and it will also again evaluate to 17. So we don't have to ship. Oh, and by the way, this is the history of how I've evaluated it, which reduces the amount of data. And it reduces greatly the overheads incurred by, Farhad realizes that the output is actually 18. And now we have to start a reconciliation process to figure out who's actually right. And that's actually a costly factor in today's financial systems. So we can avoid that by using deterministic computation. Okay, so that's so far the high-level part. To make this a bit more interesting, I thought let's move into a coding session. And, well, since Martin is an enthusiastic cyclist. His bike unfortunately broke down. We now want to get it fixed. Fixing, of course, costs money, and therefore let's first talk about money. So what you see here is Visual Studio Code. The ID, well, we've basically written a extension to Visual Studio Code such that you can get nice Daml, a nice Daml IDE out of that. The Daml syntax itself is fairly similar to Haskell, so we have a module declaration at the top. At the very top, we declare which language version that is. There are import statements. We'll make them use of them later. And you can define data types just like you do in Haskell. So this is simple enumeration. And, well, we want to represent cash, well, or money. Now, in Daml, you can't have bearer tokens. That's just getting back to the intro of the talk. We can't have that. So money is always a contract between two parties. And a party is just the unit of granularity at which we track authorization. So this can be a legal entity, but this could also be subdivisions in a legal entity, or several legal entities are represented by a single party. That's really up to the one who writes it. But so we have essentially the issuer and the owner. So imagine you get a receipt from your bank saying, yeah, you've got 200 francs. So you would set the amount to 200, the currency to Swiss francs. The owner of the money would then be you, and the issuer is the party. So this is pure data. And down here we have an example. So scenarios, we'll see that later, are essentially a way to write small programs that simulates a typical workflow that you can run through, that you can inspect and see how it works. It's essentially a test-driven development there. So, okay, this creates 200 francs for Martin, backed by bank, which we get by creating a party. So parties must be explicitly created with the get party command. And the arrow to the left is the usual Haskell do monad notation. So here we're living in the scenario monad, which is one of the monads that we have. And pure is essentially the same thing as Haskell switcher. Syntactically, what is different is in Haskell, you would probably write curly braces here. We've replaced that with a with keyword. And you would write double colon to give a type. In Daml, a single colon is enough. So that's what we started. But this is just a piece of data, right? And we want to make this into a smart contract. And that is basically done by not declaring data, a cache as a type, but cache as a template. And that cache, oh, we don't need the data type up there because the template implicitly declares the data type that we see up here. Now, what we can do with such a template is we can actually declare who may have obligations arising out of this, of a contract that stores this particular amount of data. And these are called the signatories of the contract. And we just list them afterwards. So the bank certainly has an obligation towards the party, because I mean the party could just show this as a proof of, oh, here's my proof that I own 200 francs, and that other party may then do something and ask, okay, yeah, please give me the money. We could also make the owner signatory because, well, as an owner, you're obliged to pay wealth tax, so you don't want the bank unilaterally just giving you money. But for simplicity, let's just say, okay, we only have a single issuer here as the one who's obliged. Conversely, the owner should learn that it has money, right? And that is declared with the observer keyword. That takes a list of parties technically, but we can also omit the injection into list. So we and that will tell Daml that everyone who, well, the owner will be notified when such a template cache, when a cache contract is being created on the ledger, or when it's being spent. And that will allow the owner to react to those kind of things. And now, of course, one important thing, well, let's start. Let's see, so here we have still created a cache down here, but this is a cache value. It's not yet a contract. We haven't created that. To create a contract, we want to submit something and say the bank can create a cache. And what that does is basically it creates a contract. We can actually run this part within Visual Studio, and then we will see on the right what is the current state of the ledger. And here we see that, well, we have contract of type cache in the module byte shop with the fields set as here. So the issuer is the Swiss bank, owner is the Martin. We're having a currency of Swiss francs of 200. And this is contract ID 00, and Martin knows about it, and Swiss bank knows about it. So if we had omitted the observer here, only the Swiss bank would know about it. In particular, the bike shop doesn't know about it. So far, there is something like that. We could also try out what happens if Martin just wants to create the money out of thin air without getting anything. And then we get an error here on the right-hand side. It says, oh, here we have a transaction, the bike shop, you want to create cache with those values. And up here it says, well, this failed due to a missing authorization from bank. So we require the authorization of all the signatories to create that, because that ensures, well, or let's put it out. The signatories are all those who can be obliged by that contract legally, and therefore they have to give their consent to enter that obligation. And in that case, it would be the bank. And so far, here we're saying, oh, Martin is doing that part to create cache. That means Martin hasn't gotten the consent of the bank. And so we get an error, and that won't happen. We change it back to bank. We're good again. Right. So that is how to create money. Now we also want to spend that money. And this is what you can actually do with it. So we can attach to this template, which so far was data, plus some authorization rules, plus some visibility rules. We can actually extend that with people who can do things. And this is called basically a choice. So we can say, okay, you can transfer that money to someone else. Well, and sorry. And what who is allowed to do that is done by the controller. Well, probably the owner should be allowed to spend that money. And what do we do? Well, what we do in here, and here you see a monad syntax again. So this is again a do block. We're saying, oh, please do create, well, the same thing as we currently have, a cache, but update the new owner. What choices implicitly do is they archive the current thing. So this doesn't create money out of thin air, and we can give it a try. So Martin can now exercise his choice on the cache. And the choice we call transfer. Let's say, for simplicity, we have only one. He wants to pay the bike shop. What doesn't work at the moment is, well, we get an error here about some type mismatch. And what we currently see here is, well, exercise actually expects a contract ID of some type, and we're providing a cache. So we distinguish here between the data values, which is what we have with cache, and the contract IDs that refer to these things on the ledger, and this would be hash 00. So the submit actually returns, or the create as a type, returns the ID of the created contract. And so as this is a do block, we can also bind it here, put it here. And as you've seen this compile, and now we've got a different contract here. So here's the ID. It's now 11. The new owner is the bike shop, and he owns 200 francs. That whole thing is visible to Martin, the Swiss bank, and the bike shop. So the bike shop sees it because the bike shop is the owner. The bank sees it because the bank is the issuer and therefore signatory. And Martin sees that because Martin just knows that it exists, because it has seen that as part of this, well, Martin created that by himself, basically. We can now also look at the archived parts.
Can I ask a question?
Yeah, absolutely.
Sorry, before you try to create cache with Martin, before you implemented the transfer.
Yep.
And I didn't get how you limited this ability to the bank. So,
oh, right. So, okay. What I did was, let's briefly comment that out. So this is where we started. You can forget about the transfer. What I did was, well, if we comment out the observer here, then only the bank is the only signatory. Martin is mentioned in the data, but I mean, I can have a on-ledger contract with whomever I think makes sense, mentioning other people, and they don't immediately become aware of that. That can be just a bilateral discussion with Farhad, for example. So just mentioning a party doesn't disclose that information to that party.
Oh, I see.
You really have to. That's where we say, okay, this is data up here. And then we extend that with things like signatory and observers and choices to actually make that into a smart contract platform.
Okay, I didn't see that you instantiated them differently. Okay, I see it below. Yeah,
Clear. Perfect. Yeah, thanks for asking. So back to where we were. So Martin sees that because Martin has created that thing. And if I click on show archived here, then I see that the old cash contract between Martin and the bank is struck through. So this means it's archived. It is still on the ledger because the ledger is append only, but it contains a record of this money has been spent, and the money now belongs to the bike shop. Questions so far?
I've received one question on the chat from someone. So the question is, it's got to do with the beginning of your talk. Isn't lazy evaluation one of the biggest advantages of Haskell? Example, the ability to define potentially infinite data structures.
Well,
I guess he's asking, why is it not there in Daml?
So a problem with infinite data, well, the question is, do you want to have infinite data structures on a ledger, right? I mean, it's great to have them in memory, but if you want to serialize them and ship them around in a distributed setting, you need to have an encoding for them, right? And laziness doesn't give you such an encoding for free. You would have to really dig down and implement the whole thing in your intermediate language. So it doesn't really fit the application use case. Of course, if you need something like an infinite data structure, you can implement it yourself. Because an infinite data structure, at least if you talk about pure data structure, is nothing but, well, you need some sort of laziness or some generated pattern. Like you can do a unit closure and you get lazy evaluation, where you can actually control when things are evaluated. The problem is these become function closures. So this becomes higher order data, and higher order data is very hard to ship around. So yeah, that's a deliberate choice that we haven't incorporated that because it just doesn't fit the domain.
Great. Thanks, Andreas. That's what the student says. Thank you.
You're welcome. All right, we're almost at 5 minutes to 4, and Farhad said that this is a good time to have a break. So I suggest we have, what's the usual thing, 10 minutes?
10 minutes, yeah.
All
so let's
right.
have a break now. So it's 53. Let's have a break till 3 past 4.
Right, and then I'll continue with the bike shop example. We'll see a few more things. That's probably going to take us until Farhad wraps the course up. And in the exercise session, I plan to talk about Canton. So see you in 10 minutes.
Okay, everyone, it's 4:03. Let's continue with the guest lecture. Andreas, are you there?
Yeah, now I'm unmuted.
Great.
Should work. Perfect.
Great, yeah,
So,
I can hear you.
brief reminder where we started out. We have defined a cache contract and written a few things in a scenario. And Martin has transferred the money to the bike shop. But of course, that should only come as a result of a bike repair contract between the bike shop and the bike owner. So in the break, I've briefly defined another template where we have a bike shop owner entering a contract with a bike owner with some description and some price and some payment where it's due. And this is now actually the representation of a legal contract. So legally, a contract is always between two parties. So we make those both parties signatories, the bike shop and the bike owner. Now, of course, we want to create that essentially. So a bike repair with, so the bike shop is obviously the bike shop that Martin brings its bike to. The bike owner is Martin. The description is whatever needs to be fixed. Let's say fix the brakes. Price, well, for the sake of simplicity, let's just say these are very expensive brakes, and we need a date when Martin is supposed to pay that. So we could say, okay, this is this year in May 31st. Or we could just say, okay, yeah, let's now create that. So submit. Well, who do we put there? Martin. We create a bike repair. And it doesn't like something. So that is a typo. Well, it should have bike shop. Now I'm a bit confused. Now it says it doesn't have bike error. Come on. Well, we can also do a simple trick and copy paste that from somewhere else and see whether that helps. That helps.
Could it be because the bike shop was alias, because you're using it as the name of this reference? And
problem. My guess is that the 200 might have been a problem. And of course the date is still the wrong one. Anyway, the point of the whole thing is, so if Martin tries to create this contract unilaterally, we get again into an authorization error that we see here on the right. We don't have the authority of the bike shop, right? If we put the bike shop here, we get the symmetric problem that Martin hasn't agreed to that contract. And this is actually also what happens in legal practice. You need two steps to create a legal contract. You need an offer and you need an acceptance. And you actually have to model it the same way in Daml. So we need a template for modeling a bike repair proposal that has a proposer, that's a party, a receiver, It's also a party, and a proposal, which is a bike repair data object, where the signatory is obviously the proposer, so he's going to be bound to the proposal, and the proposal will be sent to the receiver, so the receiver becomes the signatory. And now we can actually write out this as a, well, almost. We can write out creating the proposal. So it's not creating a bike repair, it's creating a bike repair proposal with the proposer is the bike shop, and the receiver is Martin, and the proposal is the bike repair. And suddenly, Daml is happy again, it compiles, and we get this proposal that we see here on the right. As usual, it's visible to Martin and the bike shop with the receiver Martin. And now we want that Martin has the ability to accept that. So that comes as a choice that we've seen. So there's a choice accept. And that will create a contract ID of a stop, wrong template. Of course, Martin should be able to accept the not the repair contract. And that will create a bike repair contract. Controller is the receiver. And we do, well, unsurprisingly, create the proposal, what we have down there. And so Martin can exercise, and here we need to bind it again. This is the bike repair proposal ID. The accept choice. And if that happens, now we end up with a correctly authorized bike repair. And on that, Martin could now get a payment method. So Martin can pay things that will not return anything, but of course we can say, okay, what is being paid? And here we now see the composability aspect. As usual, please interrupt me if needed. So Martin can choose what money equivalent, so what cash it uses, and so we can exercise, so wait, we need the controller, that's obviously the bike owner. We can exercise the choice on the cash contract, which we have written before the break, namely transferring with new owner equals the bike owner. And in the end say, oh, we don't need that. What is wrong here again? Let's do indentation. So Daml, like Haskell, is sensitive to indentation. And here we have, well, inside the where block, we need to indent stuff. Great. So Martin need not only submit the proposal, accept the bike repair, but Martin can also pay the whole thing. So this will get us the proposal, the contract, on the contract, can do with cash, and it can take its cash ID. And now the money is again with the bike shop. If we look at what has happened over time, we will see that there was a bike repair contract that's now archived between Martin and the bike shop. So all obligations from that have disappeared because Martin has paid. We have the proposal that was an intermediate step to create that one. And we have the two contracts of the cash, the original one that was archived and the new one that's still active, saying that the bike shop has that money. Now, what we haven't done yet, and this is a severe flaw, is, well, suppose that Martin only owns 50 francs, but the price is 200. And now, well, if we look at what the outcome is, the bike shop owns 50. So we actually should have made sure that the money that is being used to settle the outstanding payment actually has the right amount of money that we expect. To do that, well, as you see, this is a contract ID. It just refers to a contract, and this and going from an ID to a contract depends on ledger state, right? So we can't just say, oh, cash dot amount. So we could write something, try to write something like, we want to assert that the amount that we're paying is the price, right? That doesn't tie it because it will say, oh, the amount is not a record field of the cash because cash is a contract ID. So we need to go to the ledger and actually look at the contents. And that is done by the function fetch. And we can say, oh, then we can check that the cash is equal to the amount. And we might also want to check that the currency is Swiss francs, which we have implicitly assumed in the bytecode. And if we do that again, we're back into this land where we see, oh, this is some assertion has actually failed. We came up to the fetch. That is the partial transaction, and here you see a text representation of all the transactions that have happened so far. If we change that back to 200, then we get back and the shop gets started. Of course, you can make this example into an even more and more elaborate example where you can then say, oh, okay, I'll give you a change, or you just have to split money first, or whatever. We could do that, but I guess you've already seen the kind of flavor of programs that you can write. What you haven't seen is that you can actually do some sort of computation with this. This was really just defining data types and moving them around between people and getting familiar with the authorization logic that we have. Questions so far? Well, if not, then that completes the first part. As said, if you want to find more about Daml, play with it, go to daml.com, you'll find enough resources there. Question is now, how do we actually run this in a distributed system? And that's what Canton is about. So what you've seen here with those scenarios that we run, that is actually just an in-memory execution on my laptop. you can't connect that one to a distributed system. Canton gives you the opportunity to do so. So if you're looking for a bunch of resources, you can go to canton.io, which contains both the software. So Daml itself is open source. Canton is, well, you can get the release for free, but it's not yet open source. There are plans to go open source as well, but we're not there yet. On the web page, you can find a demo that is more focused on what you can actually do with it. So there's a healthcare example. There's also a recording with it. So you can have a look at it if you don't want to explore it yourself. If you have questions about that, go to the same forum or Slack channel as for Daml. The same people are listening there. I want to mention that I sent Farhad a small exercise sheet for the end of, well, for this. That gives you a few hints what you can try out and play a bit with Daml if you're interested. In this talk, and I guess I'll start before the break or before handing over to Farhad. This will be more of a high-level introduction. What are the concepts that we've seen as code now in a more abstract setting, and how does Canton work internally? So, just as a reminder where we're coming from, so we're talking about smart contract platforms, of essentially breaking the silos of where every party wants to keep their own database into somewhere where we have a shared database or a ledger, right? We've seen that we need to deal with read and write authorization. We haven't talked yet really about how to achieve scalability. And one thing that we want to avoid is that we create even bigger silos, which is what I hinted at with global composability. Well, if party A is member of several multi-party workflows, of course, party A doesn't want to have to connect to 3 different or 10 different ledgers. The solution that we've seen so far with Daml is basically this abstraction that it feels like you're writing against a shared database, and you get the read and authorization rules and what you can do there. And then we need to have an implementation. And the implementation basically replaces this idea of a shared database with something that you actually can run in a distributed setting. So we have those participant nodes, which basically provide to the party what we call the ledger API, and this is their means to access this shared database. So on the very primitive side, you can send write commands by similar to those submit things that we have seen in scenario monad. The participant will then engage in a synchronization protocol with all other participants and whatever components are in this cloud. And as a result, well, the participants will then inform the parties, oh, this has happened. Here's a stream of updates since you've last looked. And the party can then update its own local view, react to whatever happens. Of course, this should achieve certain goals. We want to implement this abstraction faithfully, and there are some limitations to that. So if you have ever heard about distributed systems, you've certainly heard about the cap theorem, that you can't achieve consistency, availability in the presence of network partitioning. So there are there's some fine print to that. We also need some reasonable trust assumptions for the whole thing, and this is where different synchronization protocols can provide different guarantees. And we want to solve the composability and scalability issue. And before the break, I'll just revisit the abstraction at a higher level than what we've seen in the code. This is what we call the Daml ledger model that is described in more detail on the contents page of the documentation. So we'll have hierarchical transaction. That's basically what you have seen. So we can look at those transactions. And here we see that, oh, we have a transaction that has several children, which do a fetch, which do exercise. And as part of the exercise, we have another sub thing called doing a create. Right? So we can represent that visually as a tree. And the Daml programs essentially are translated into these trees by the Daml runtime. And these trees, they have on the nodes some labels on the actions, what happens with the data. And the data has this read and write authorization to get the integrity and confidentiality properties, like the signatory, if data 1 specifies that this action needs the authorization of Alice and Bob, because they're the controllers on the exercise, then that's on there. And then there's essentially the signatory and observer story, which tells us who may see, who must be informed about certain actions happening on that data. And that gives us the abstraction that we can then compose into a ledger structure. So in this example, we'll look at abstractly at 3 parties: Alice, Bob, or the bank, and Carol, bike shop owner. And rather than looking at a complicated cache thing, we'll look at a token, and you can imagine a token being just a cash contract with value 1 franc. So we fixed the currency and we fixed the amount. And in the notation, we'll use a $sign to mark the signatories, and we underline the observers. So this is a reduced cash contract. And now we can think of a ledger as essentially a sequence of transactions that are submitted by a party. So the bank, they can create a token with itself as signatory and Alice as the observer. And from a global ledger states view, so we start with, oh, there are no contracts on the ledger. And after this transaction, we've got a single token contract. And then Alice could transfer the token to the bike shop B by exercising the transfer choice on that contract. And that creates a new token. As a result, this input contract is being consumed, and we create a new one. So in terms of distributed ledger, this is an unspent transaction output model, the same as is being used with Bitcoin. In particular, once some contract is on the ledger, it's immutable, unlike in Ethereum where you can update the state. But you can do it one way or the other, so the two are essentially interchangeable in terms of expressivity. Right, so you see here who needs to, who submits that, and so we can continue that ledger. In a more complicated thing, so suppose we have 2 tokens, and this goes now towards the atomic swap. 2 tokens issued by D and C to A and B respectively, and we have an offer or a proposal from A towards B to swap token C against a token for D, backed by D. And such a swap would consist of 2 transfers. One transfer, one where A transfers the token to B, and one where B transfers the token to A. Everything wrapped as a consequence of a big choice except, which settles the 2 things. And as a result, it would consume those 3 contracts and generate those new tokens with a new assignment. And the guarantee here is that this part happens atomically. What I said earlier, we can't end up with this part happening and that part not happening. So it takes essentially away the counterparty risk in those transactions because we can do them atomically. Right, and then we can define what a valid ledger is once we have this structure. And we've defined that as the intersection of three properties. One property is authorization, and we've looked into that quite a bit. It's this signatories, observers, and signatories and controllers need to authorize the consequences, and authorization flows. We haven't talked much about that, but just as in the transfer choice, right? So we're creating here a new money, a new cash contract as part of the transfer. We certainly have the authority of the owner because the owner is the controller of the choice. But in order to create that, we actually also need the authority of the issuer, because the issuer will be obliged to pay the new owner the amount that's being specified. But this is fine because the issuer has consented to the creation of this cash contract, and therefore it implicitly consents to all the consequences that this contract may have. In particular, it knows about, oh, there is this transfer, and this transfer is fine because, oh, I know that this spends the amount for the current owner and just assigns it to a new owner, so I should be fine with that. So the signatories flow into they implicitly authorize the immediate consequences. Right, so this is authorization. We need things to be conformant to a model, and this is basically what we specify here in Daml. Conformance, for example, includes that this assertion must hold, that the money that's being used to pay the bike repair is actually the money that was specified and the amount that was specified, and everything else. And then there's consistency, and consistency mainly means, oh, you can't spend your contract twice. So where did we end up with? Right, in the table view. So this archive cash contract, I can't spend again. We can actually try that out. So it could, on the cash ID, do a transfer when it's new owner. So if it tries to do that once again, we see that we get an error saying, oh, you're trying to exercise choice on a consumed contract or was previously consumed by that other sub-transaction. And that is basically preventing double spends or creating money out of thin air. Why have I written that? I mean, it's the same as that down here. Anyway, you know what I mean. So that's that. So in particular, as a consequence, we want to guarantee that, or the rules on the ledger guarantee that if there is a valid ledger and I'm following the Daml protocol, then I can be sure that no rights will be taken away from me, so no choices. No obligations being imposed on me, so I can't become a signatory without having consented to it. And neither can my counterparties remove their existing obligations without me agreeing to that. And that's the abstraction that we get. So from the right authorization, we can also get some sort of read authorization, meaning the visibility. That's what the observers are about, plus the signatories. and the actors that the actors are essentially the controllers. And so a transaction like that will be chopped up into many pieces. For example, the offer contract that does the swap, like the bike repair contract, is only visible to Alice and Bob, but not the bank. And then there are the sub-transactions, and these sub-transactions, green box on the left is only visible to C, because C is involved here as a signatory, but D has no business with that. And conversely, D over here obviously sees that part, but Carol can't see it. We can also see that in our bike shop proposal. So you will see that the bike repair is not visible to the bank, even though there was this one transaction that involved both the bank and the two signatories of the bike repair contract. Right, and this is, I think, a good time to stop. After the Farhad wraps up the lecture, I'll go into how that actually translates and is implemented in Canton. But Farhad, over to you.
Thank you very much, Andreas. So, sorry for the interruption. I just wanted to conclude this course from my point of view before the start of the next exercise session, since some of you may not be able to attend it. So, thank you for your attention semester. It's been a bit of a strange semester. I think all of you will agree with me. Lots of things have happened. By the way, can you see my slides or the web page?
Yes.
Great. Okay. Yeah, so I just want to have a quick overview of the topics that we've just taken a look at over these 3 or 4 months. Yeah, we started off with programming paradigms, formal proof, the sequent calculus, then we went down to propositional calculus, then first order predicate calculus, just getting a bit of muscles working again, then the lambda calculus, and then we had a bit of a break because of the pandemic that just happened, and then we had to switch to online lectures, and then we started functional programming. It also stuff, Haskell. We talked about the spring break, more functional programming, yeah, monads. We talked about reasoning about programs with Isabel Hall. We took a look at quick check. Oh, by the way, I just wanted to mention to you, you may have seen Andreas before. So in my page on reasoning about functional programs, there's a video there, and this is Andreas. So yeah, if you think that I've seen this person before, you have. Yeah, so he was the presenter of the video functional programming and proving in Isabel Hall. So anyway, so this is you may think that this course was a bit of a mixed bag with many different things, but actually these things are related because the community behind it is they work on the same things, and you here is explaining to you things in distributed computing, but it's from the point of view of someone who is really into programming languages. So it's I hope that you've enjoyed this, and yeah, I would like you. So I'll give you some time for this as well. I'd like you to fill out this little feedback, but yeah, that's going to come. Let me just share my slides for my conclusion quickly. Yeah, so one thing is that people normally ask me about the exam. Now, the exam is actually nothing that you should be worried about. If you participated actively in the lecture and the exercise session, as I told you before, the exam is quite straightforward. I've also given you a model exam on Moodle. Take a look at it. You'll know what I'm talking about. Typically, people finish the exam way ahead of time. Yeah. So I guess it's one of those exams where if you can do it, you'll do it ahead of time. If you can't, you'll struggle. Yeah, but I think that's fair. The exam will be in English, just like the course, and you may answer in English or German, and it'll be closed book. Yeah, some final words from my side. So I hope that you enjoyed taking this course as much as I enjoyed giving it. Well, this course changes from semester to semester, but still we have just scratched the surface of this area of computer science. So programming languages, the intersection between programming languages, formal verification, software engineering, sometimes even distributed systems. Yeah, it's very interesting. I hope that I've succeeded in sparking your interest in this fascinating area of software engineering. Yeah, so much more is not possible in this brief of time. Yeah, I mean, as Andreas and me both can probably testify to, this is an area that you can spend years and decades working in. In case you have further interest in this area, please contact me for Studienarbeit or Bachelorarbeit and Master Studies. And at the beginning of the course, we talked about this this idea that if all you have is a hammer, everything looks like a nail. So I hope that I leave you with a more complete toolbox to take on your challenges as a software engineer later. For myself, I can claim that fluency in formal methods, logic, and functional programming has severely increased the simplicity and quality of my work as an engineer. So this is something that I would like to give the people who are leaving the HSR. And I hope that the concepts you have seen here will be helpful to you in your future work as engineers. I'd like to leave you with a quote. It is not this is from E.W. Dijkstra. So it's not the violin that shapes the violinist. We are all shaped by the tools we train ourselves to use. And in this respect, programming languages have a devious influence. They shape our thinking habits. So the claim is here that if we use more rigorous programming languages, they will force us to think in a more rigorous and complete manner. So I strongly advocate the use of such programming languages, or at least learning them, so you can think in a certain way. Good. I'd like to now ask all of you, I'm going to give you about 5 minutes to do this. I would like to ask you, I'm going to change my screen sharing again. Sorry about that. I'd like to ask you to fill out this questionnaire. I'm going to just put it up right now. You can go to Moodle. And it's here, this short 3-minute course feedback. I'm not a big fan of so long drawn out feedbacks. As you know, this course, I pretty much try to keep it in tune to the interests of the students. So I'd like to have some feedback on this. Of course, this was a strange semester, but still. So they're just 3 very simple questions. Did you like the course? Yeah. So yes, mostly so, not really no. Yeah? What did you like? What did you not like? And do you have any additional remarks, suggestions, or recommendations to make this course better? And if so, just let me know. I'm going to give you 5 minutes to do this. So it's 41. Let's come back here at 46, and then I'll formally conclude the course. So you have, yeah, 5, 6 to fill this. I'd like to do it, you to do it right now because, yeah, then I have some feedback for the next time I do it. So thank you very much for for participating in the feedback. For those of you who will not be able to take part at 5 o'clock for the continuation of Andreas's talk, I'd like to thank you for your interest and enthusiasm for this call, and to wish you pleasant holidays with your friends. Good. Thank you very much. I'll see you, I guess, next during the Beratungswoche. Of course, you can always send me questions online. See you. Bye-bye. Yeah, and regarding the continuation of our course, I guess we'll start again at 5. Is that okay with you, Andreas?
Sure. I mean, it's also fine to start immediately, but what do you think makes more sense?
I think let's take a 10-minute break. That
All
would
right.
give people time to
Yeah.
step out a little.
Oh.
I'm continuing the recording. I don't want to pause it or anything, so that I guess you can cut it later on, because I'm a bit scared of
Sure.
touching anything. Okay, good. Okay, it's 5 o'clock now. I would say let's carry on with the guest lecture. Andreas, is that okay with you?
Absolutely.
Great.
So welcome back. Thanks to those who stayed around or who are going to listen in later. So I stole Farhad's screen share again, so I hope you can see the slides again. Right, I mentioned how do we implement this abstraction in a distributed setting? Well, a trivial solution would be to find a trusted third party to run the database. Then all problems would be gone. Well, not all of them, of course. We precisely have to find a trusted third party, and it's extremely unlikely that we can find a party that everyone agrees to. Of course, you can mitigate that by doing some kind of distributed replication, Byzantine fault tolerant, whatever. But if you have a data breach on the central instance, then that's a single point of failure. So you will leak all data there. And it's not really composable because naturally we will have several trusted third party evolving. And so we just end up with bigger silos that we wanted to eliminate in the first place. So another alternative to implementing a distributed database is essentially state machine replication. For those who have never heard about that, here's a quick refresher. So we assume that we have an atomic input, a common input sequence to all replicas. So you can just consider this as a stream and all agree on that. So we have essentially an ordering service or an atomic broadcast system. And then we have deterministic machines. They implement essentially the state machine. And because they're just deterministic and they receive the inputs in the same order, we know that the outputs are consistent. So they will all first say, here's a duck, then there's a teddy bear, and then there's a ball. Of course, some machines may lag behind others a bit. So they may only end up being with the teddy bear and not yet having reached the ball. But that is essentially the underlying principle of blockchain technology. Like Bitcoin, like Ethereum, like essentially everything else is that you do that. The only problem with that is this only works if we have the shared globally replicated. That's the reason why if you want to run your Bitcoin client, you need several gigabytes of memory just to keep the past history, even though you have never interacted with the system, just because that's part of the past history and everyone has to process every piece of data. That's not really scalable. So let's look for something else, atomic commit rather than distributed ordering. So in order to prepare to run a protocol over Canton, we prepared a transaction. So this is what we had before the lecture, the swap of two tokens. That's getting chopped up according to who needs to receive what. So in this case, for example, the create token will be sent to Bob and Carol, definitely, because Carol is a signatory and Bob is an observer, so we can compute that. And, well, this box, well, is part of what is being sent. But of course, there's also a bigger thing that needs to be sent, and that needs to be sent to Alice and Carol. The exercise of that does the token transfer. Because Alice and Carol are the signatories, and Alice is the controller of the choice. And the green box implicitly includes the orange, the red box. And similarly on the right, this is symmetric. And then there's the big blue box that is sent to only to Alice and Bob, because they're the stakeholders of the offer contract. And now this gets sent off. And how this looks like as an atomic commit protocol is basically, here we have a message sequence chart. So Bob is the controller and therefore has to commit the whole thing. And there's a prepare phase. So Bob sends it to what we call a synchronization domain, and this is essentially the ordering service and the commit coordinator that we're using. So the ordering service is called the sequencer, and the commit coordinator is the mediator. So the sequencer will assign a timestamp, and the sequencer will assign timestamps to all messages, and the sequencer will ensure that the recipients will receive messages in timestamp order, and the sequencer will only assign every timestamp once. So it distributes the different packets into which this transaction was split up to the different recipients with the timestamp, and the mediator also gets it, and the mediator will just enter it into its records. And then there comes the validation phase. In the validation phase, this is actually where the other participant, and Bob as well, check that this will not violate the validity of the ledger. So this includes checking that whatever Bob wants to do is correct with respect to the authorization rules. It corresponds to what the Daml model program code prescribes, and all the inputs of the transaction, so the contracts that are being used, that are being fetched, that Bob does an exercise on, they're all still active and none of them is archived. Wow. And if all that works, and so these are essentially the integrity and authorization checks, then they will reply, yes, I'm happy with the transaction. Whereas otherwise, if something's wrong, they can respond with no and have to give a reason. Now, all these messages are sent back to the sequencer, and the sequencer simply forwards them to the mediator. And the mediator just collects those messages until it has received enough of them to come to a decision. And this is then where we enter the commit or abort phase. The mediator will then decide whether the transaction should be committed or aborted. In case of a commit, all the participants will receive that commit with a timestamp, and therefore know, okay, from this point in time onwards, I'm supposed to consider this transaction as being committed, and then they can carry out that on their local copies. But if it's a rollback, then they know that this transaction will not have any facts. They can release all sorts of locking or stuff that they need internally to manage that, and they can, and Bob can then output to the application, oh, by the way, this has failed, sorry. Whereas the others, in case of a success, can output, oh, by the way, this is a new ledger state update that might be relevant for you. So in terms of atomic commit, this is a classic two-phase commit, with the first phase going until the mediator decides, and the commit phase starting from when the mediator decides to commit the whole thing. Right, so this was described for a single domain with a single sequencer and a single mediator. But notice that, well, what we do need here is only the ordering on the sequencer, and we only need to collect data on who needs to confirm and that kind of things. But we don't need to store the actual contract data on the synchronization domain. And that's why domains aren't becoming our new information silos as they would with a shared database. Instead, you can just create a new domain whenever you need. And several participants can do a joint transaction if they have a common domain. So those three participants, for example, they could use this domain to run their workflow in one transaction. And then later, if, say, this participant wants to use an output with that participant, we could choose between those two domains. That provides us essentially a way to mitigate the trust assumption on the domain. Namely, well, if you don't trust that domain, then you can just spawn up a bilateral domain and run your workflow there. And it also provides the key to scalability, because whatever happens on two different domains is conceptually unordered. So you can run the processing in parallel, provided that you have enough local resources, but that means you can do horizontal scaling. And therefore, we don't end up being locked into some sequential bottleneck. Right.
Can I ask you something?
Absolutely.
So when you go back to the atomic commit protocol slide before, when you talk about domains, it's the synchronization domain. So one of these domain circles contains the sequencer and the mediator.
Exactly.
Okay. And the reason why each of these nodes do not have to store the whole state, like in the case of blockchain, is that only the domains have to store this, but the participants do not. So could I think of a participant like a Bitcoin
No.
wallet?
It's the other way around. The participants store all the data that they need.
Okay.
Right. So there is essentially this idea. We have this idea thanks to the signatories and the observers, that we exactly know who needs to be informed about that change. And due to the authorization rules, that ensures that, well, we can compute who needs to be informed about that. And only those people need to be informed about that. Now, we still need to solve the conflict problem of, well, if two people concurrently submit something that both consume a contract, say, then only one of them can win, right? Otherwise, we have a double spend problem, and that's not good, right? So we need to define an order between those things, and this is what the sequencer does by assigning those timestamps. And well, as you see, Carol and Donald never have to talk to each other directly. That means Carol doesn't need to know that Donald is involved, and Donald doesn't need to know that Carol is involved. And that's essentially one of the roles of the mediator, to guarantee these, to ensure this privacy between unrelated parts of the transaction.
Okay, got it. Thanks. Can I ask you another question then?
Of course.
Great. What you said that this is how the double spending problem is solved, but I could have two domains talking to the same two participants.
Yeah.
And what happens then? Who wins? Which domain would win then?
So that's that here. We said, okay, well, you can do a transaction, and so suppose we have a transaction between these two participants that I'm showing. Then they could choose between these two domains, right? But technically, a contract always resides only on one domain. So if they want to use it on another domain, they themselves have to provide a synchronization, right? And Canton has a synchronization protocol for that. And that just ensures that, yeah, you detect those conflicts, right? So basically, well, if the contract, say, resides on that domain, but I want to use it in a transaction on that domain, what happens is that you first have to lock that contract here. And in order to use it, you have to provide a proof that you've locked it. And then the other participant, if it concurrently tries to use it here, will realize, oh, this contract has been locked. And therefore, depending on whether the lock was granted first or the transaction was being sequenced first, we detect that conflict.
Okay, got it. So a contract also has to specify the domain on which it should be executed.
Well, there's basically a large, well, there are heuristics that automatically distribute things. So normally what you would do is you would partition, or you would look at your workflow and then figure out which part of the workflow should be run over which domain. For example, you have a domain that you use to manage your bike repair orders, and you have another domain on which you manage your bank account, right?
Mm-hmm.
Say because this is the bank, and the bank doesn't even need to be connected to where you manage your bike repair orders.
Mm-hmm.
Then you would just have a transaction that is either sequenced there or there, but the parts that are visible to the bank, they must be run on that domain.
Mm-hmm.
And the point of why you do that is, well, you want, as you see, synchronizing between domains is somewhat of a costly process.
Mm-hmm.
So you want to run as much as possible on a single domain. So if you were to just do it randomly and flip a coin, you would just end up with loads of cross-domain synchronization.
Mm-hmm.
So if you really build your workflow, think about it. Okay, these steps, they go to this domain, then we're done, and that the next part of the workflow will be done on another, and that gives a clear assignment. It's like pinning your programs to cores on your processor. Mm-hmm. If you really want to have good performance, you want to have a dedicated core and avoid context switches.
Okay, I think I understand it now. So the participants only store the information that's relevant to them, and the domains are basically in charge of the execution.
No, the domains are really just in charge of sequencing and collecting these responses and issuing the verdict.
Yes.
They in particular don't store the data.
Yeah. Okay.
And that is the core, right? So I said, okay, a contract resides on a domain, but where the contract resides is essentially an agreement between the signatories, right? So we basically have a consensus among, say, those two participants that this contract is currently residing there. But it doesn't have to be stored on the domain. It's just that those two agree, yeah, we use this domain for dealing with that contract. And if you want to use it somewhere else, you need to involve that domain into the protocol.
Okay. Thanks.
You're welcome. Right. So what can be a domain? Well, you can simply implement that on a SQL database. And then you've got a very simple, very efficient structure. But of course, if your database blows up, then your domain becomes unavailable. If you're worried about bugs in the database or the domain administrator having access to the domain and therefore treating you unfavorably, you can go to what you always do when you need to distribute your trust you replicate things, right? So you could run a classic BFT protocol. You could run a proof of work to improve the integrity constraints that we get from the sequencer and the mediator working correctly. And this is what we've actually done. So in Canton, we have an implementation that runs on a database, but we also have an implementation that works with Fabric and with Ethereum, and they have classic proof of work. So you get the sequencing guarantees by getting agreement there. It's more expensive because you're doing more computation, obviously. And this goes to what I just told to Farhad's or reply to Farhad's question. So our data that we actually ship over domain is encrypted. So you don't have to provide the whole global state. In particular, the 200 francs that Martin pays for fixing the brakes, they won't be visible to the sequencer nor the mediator. They're just encrypted because that doesn't matter to them. They don't need to check what contracts are being used. It is all done on the participant. Sequence is ready just for ordering. And that gives us the strong privacy guarantees. So there's no single point of data where stuff is stored. And of course, as I said, every domain may be a ledger in its own right. So a Fabric ledger is a ledger, and we just use that as backend. And then there are these cross-domain transactions that I told for the previous, talked about on the previous slide to Farhad's question, that allow you to use a contract on one that's created in one domain on another domain. And if you think of, oh, these are different ledgers like Ethereum versus Fabric, then we get an interoperability protocol between ledgers. Of course, that's not a true interoperability protocol with the native assets that you keep on the ledger, like the Ethereum contracts with the Ether in there, or the Fabric contracts. This is only interoperability between the Daml parts on those ledgers. There might be eventually a possibility to do that, but that would then certainly be a specific solution to the particular ledger that needs a custom integration. Right, so what are actually the trust assumptions on the whole part? Well, we allow arbitrary Byzantine participants. So they can crash, they can have bugs, they can maliciously send the wrong answer, whatever they want. And of course, if you as a party communicate with a wrong participant, you don't really get much guarantees because, well, you're completely dependent on that participant node. You can check that, oh, this actually behaves according to the specification, but you can't prevent it from misbehaving, unless you run it yourself, of course. Communication between all components is encrypted, so we use TLS in the implementation. But basically, these are secure channels. They seem to be asynchronous, so messages may get delayed, and the protocol has to cope with that. The domain has to satisfy higher trust assumptions, so we assume that it's honest. That means it executes the protocol according to the specification, but it's curious. So we want to hide as much data from it as possible to not break our confidentiality promises. And as explained on the previous slide, you can do replication in order to mitigate that. You could also run it in a trusted enclave, but you need a root of trust, and that's basically here, that part. And the responsibilities, well, the participant, we've talked about that already. The participants are responsible for ensuring no double spends, so detecting all conflicts. That doesn't have to be on the domain. And for ensuring the integrity, meaning the authorization rules are respected, the contracts on the ledger and the transactions actually correspond to what was specified in the Daml model, etc., etc. The mediator also has a play in that it must make sure that everyone is actually sends an answer, because you can't hide from from Donald that Carol is involved in the transaction, and at the same time not trust the mediator to wait for Carol's answer, because Donald doesn't even know that there's need to wait for Carol's answer, right? And that gives us the privacy between the participants. And the sequencer, as I said, it just does an atomic multicast of the encrypted data, so it doesn't need to read. So what does this actually look like in terms of confidentiality, privacy, and scalability? So we already said that Alice and Bob see the whole transaction. For Carol, when she's only involved in the left branch, well, she certainly sees the left branch as her ledger. And she sees that this is embedded in a larger transaction that has some other parts there. But by using Merkle trees, these are just blinded hashes, so they don't leak any information that would be useful to Carol. the sequencer and mediator, they see the structure of the transaction and who's involved, like Alice and Bob and Carol and Donald, but they don't see what is actually being talked about. And that's important, right? So even so the structure may leak a lot, like they could see, oh, this looks like a swap transaction between Alice and Bob. The actual business details are hidden, like how much Alice pays for something and what she gets in return. And that is actually the sensitive data part here. And for scalability, well, Eric, a bystander to the transaction, is not involved at all. Of course, it can monitor the network traffic and therefore infer something, but from the protocol's perspective, Eric doesn't need to be involved. So we only need to involve the people that are actually part of the transaction. And this goes back to the very beginning, where we have built in these notions into our programming language, such that they're always available. Signatories, observers, controllers. And that gives us the scalability, because the participant as such need only do the processing that is relevant for them. There's also an integrity theorem. So this is programming languages and formal methods. So the past half an hour was more about distributed systems, so not a perfect fit to the lecture title. And the first 90 minutes was about programming language. So there's also a bit of formal methods in there. Namely, you can even state a theorem about the integrity that links the actual implementation in the Canton protocol to the abstraction that we're trying to achieve with Daml, right? So, and the theorem is essentially a safety property. Whenever you run the Canton protocol, then there is a valid ledger where, in particular, the right authorization rules hold. So the authorization works. And all parties that are honest, and the party is basically honest if its participant node is honest, like behaves according to the protocol and performs all the checks that it needs to do. Well, if you're such a party, then your view on the ledger that you get from the annotations on the actions of the ledger, that is actually what you are being served over the ledger API. So you get everything that you are supposed to get. And whenever there is something on the view, there's something in your view, then you actually have a cryptographic evidence that this is part of the ledger, like signed transactions and the like, such that you can actually go to a third party and prove in a dispute to a judge, look, this is the proof that I have, and therefore I have this right, and now let's find a solution to our dispute. Conversely, if anyone has cryptographic proof that concerns that party, with respect to a Daml action, then actually this proof is valid in the sense that the action is part of the ledger. So nobody can try to prove to you or try to make a case that you have an obligation if you haven't, actually. And, well, all the commits by that party are authentic. And that means that, well, if that party is the committer and the commit is on the ledger, then the party actually has requested that change. And the party also believes, has received the information that the commit has succeeded. And we're still in the process of actually building a rigorous mathematical formal model of that. We have pen and paper proof of that, but going from something like that to a formalizable proof is a long way, but it's still going on. And that brings me actually to the end. So in conclusion, what you've seen is Daml and how to write contracts. We had the bike shop example. I'll send the Daml file to Farhad after the lecture, such that he can upload it if in case you want to play with it, because doing that from a video is terrible. I've briefly talked you through the ledger model, which is the abstraction in terms of ledger updates with the hierarchical transactions and the visibilities. And then I've talked to you briefly through how Canton works as a distributed commit protocol that implements that thing with these global composability properties. If you want to try it out yourself, I mentioned already the web pages, daml.com for the language, Canton.io for the protocol. You will also see some explanation how Canton works in a lot more detail, and the high-level concepts are explained in the Daml lecture. And then there's this exercise sheet. Unless you have questions so far. Any questions? If not, so Farhad has uploaded an exercise sheet. And what happens in this exercise sheet is we just ask you to play a bit around. If you download the latest Canton release, then there is an example in there with an exercise, example number 6. And what that does, I'll show you briefly in a minute. So right, that's there. So this is basically the Canton release that I've just downloaded this afternoon, and that has essentially a Daml model for sending messages from a sender to a receiver. The sender can retract the message and the receiver can reply. There's a small scenario with Alice and Bob sending messages back and forth. And so you can very easily build a distributed messaging application with Daml here, running over a server. So digital asset operates what is called the global domain on Canton.global that acts as one of those synchronization domains, provides a sequencer and a mediator. So you can connect to those and use that to send the data around. And then there is essentially a README file that describes how the whole thing fits together with detailed instructions of what you can do. And just to show you how that looks a bit, so I can start Canton with the Canton configuration with some initialization script. That'll take a bit because it's building up the connection to that remote domain, synchronizes with it. The like, and then, right, I can add a name under which I want to be found. So that name is then being made into a unique name by adding some long suffix. I'll copy that for now. And that now Canton is running in the background. Now you want to also use it front end. So the Ledger API you can access either as a JSON API or via gRPC. Building a full-fledged web UI for that is a bit out of scope for an exercise. So we're using Daml Navigator, which is a generic web UI for Daml contracts. So we can run that in one of the subfolders, and then I'll have to go to this local host. on the port that's been specified. That gives me that. I can then log in as Andreas. And now I see essentially the templates that I have available. In particular, there's a message template. Then I can essentially fill out. So this is just a graphical UI to the scenario that we've seen. So what I can do here is I can take my username. I could put a receiver in there. Probably nobody's currently running that, so I'll just send myself, and I'll send myself a message. If I click send, so this now goes to this domain. I will see, oh, this I've sent that to Andreas, I've also received that, and I could manage contacts there, which I currently don't have. And right, so once you're there, you can then go through further. So we're basically down here. You can then start to extend the Daml model, upload that to make it more convenient, like having a contact, and then create that. You can also search for other people. So let's see what kind of Andreases we have. We'll see that, oh yeah, from a previous attempt I've logged in, and so there are currently 2 Andreases. Also, if you quit the whole thing, quit the navigator as well. Well, if you restart, the whole thing, your contracts or your messages will be stored locally in a database file on your machine, such that when you rerun it, you won't be asked for your username anymore, and your messages will fit it. So that's an easy start if you want to play around with that and actually get some distributed application running very quickly. So that one is running again. So first I have to log in again. My messages are still there. All right, and that concludes my part of the lecture. I'm happy to ask questions, answer questions, sorry. Or if you want to play around with it, feel free to send me an email if you need help with anything. Let us know. Also, if you run into any problems, I mean, this is under active development. We're happy to receive any kind of feedback that you'd be interested. There will also probably be a talk at ZeriHack in almost 3 weeks' time. It used to take place in Rapperswil. This year it will be online, like this lecture, where Simon Meyer will give a talk about Daml, and we might even have projects around Daml. That's it. All right. Thanks for listening in. Question time.
Great. First, let me thank you, Andreas, for the very interesting lectures. Yeah. After, at least from my point of view, there's been so much work around this, and a lot of this was not released until, I wouldn't say quite recently, but yeah, at least for me, quite recently. It was really nice to take a look at what's happening, and yeah, it was great. I mean, if I had a course called Distributed Systems and Formal Methods, this would be something that would be great to do, to put in, yeah, for maybe a couple of weeks even. Great, interesting stuff. Does anyone have any questions? I don't see anything on the chat. But yeah, it looks good. I mean, I'm looking forward to playing around with it.
All right.
Thank you very much again, Andreas.
Thanks for the invitation, Farhad.
Welcome. I'm going to stop the recording now.